morning. This audience, and especially after 4 days of this meeting, does not need any motivation in why the black holes and the Milky Way and the gravitational wave sources that Lisa hopefully will observe are connected. There is a nice coincidence that the Milky Way black hole is of exactly the same optimal mass that Lisa is tuned to discover. So what I want to, instead of making this motivational introduction, what I want to do is to try and say in a much more focused and precise way what exactly is the physical nature of the connections that we have. What is special dynamically about this lower range of black hole masses that sets them apart from more massive stars? In particular, what are the ramifications, the implications, and they are quite substantial, of our understanding of the galactic center to our ability to predict something about EMRIs and to understand Lisa sources in general. So this is going to be the first third or half of my talk, and in the remaining I will try to go through several relaxation mechanisms that are crucial for understanding EMRI dynamics, and try to describe how by the back and forth between theoretical considerations, simulations, and observation, we hope to improve our understanding of these dynamics and increase our predictive power about EMRIs. So a few basic facts. So we know that galaxies and black holes obey an empirical relation, the M-sigma relation, which has something to do with the joint formation history. We don't exactly understand how this comes about. This is one way of writing it, and for simplicity I've chosen here a nice round number for the power law, 4. It may not be exactly 4, but anything I say is not going to depend strongly on this exact value. Now imagine we have our massive black hole sitting in the bulge of a galaxy. There is a radius out of to which the black hole influences the dynamics. We call it the radius of influence. And if we can assign a well-defined value for the velocity dispersion outside this radius, the radius of influence scales so. And from, say, invoking the Viral theorem, or just, I would say it's almost intuitive, one can alternatively define the radius of influence as the radius in which the stellar mass reaches a value which is comparable to the mass of the black hole itself. Beyond that point, the black hole does not dominate the dynamics. The stars have a say as well. Now, using these two relations, you can easily calculate the mean density within this volume, and it turns out to scale inversely with the mass of the black hole. A consequence of the M-sigma relation, which tells us something which maybe is not obvious at first glance, that in fact the more massive black holes have a lower density stellar environment around them. You can also calculate what is the relaxation time due to two-body interactions, two star-star interactions. So crudely, this can be done by multiplying the density times the typical velocity between two stars times the radius at which two stars passing by each other affect each other significantly, which scales inversely as the typical velocity squared. This is the size squared is the cross-section. This kind of n v sigma kind of considerations already gives us the following scaling. So first of all, it scales inversely with the power higher than 1 probably with the mass of a black hole. So relaxed low mass galactic nuclei will have shorter relaxation times. If you go low enough in mass, the relaxation time will become shorter than the Hubble time. So based on the M-sigma relation and on the assumption, it's an assumption, it's not required to be so, that the galaxy had time to relax without being perturbed by some outside influences, we see that low mass galactic nuclei have a relaxed stellar environment around them, and it turns out, by pure coincidence, this was not, I think, definitely never played a factor in the design of Lisa, that the upper mass of typical Lisa targets is also the upper mass for those relaxed nuclei. So Lisa, in fact, will not be and at least as far as EMRIs are concerned, but probably also for, say, maybe other targets, LISA will be predominantly looking at a very special subsection of galaxies, and those are galaxies with relaxed nuclei. And because this is a special dynamical case, or so we tend to think, and the galactic center is exactly one of these types of nuclei, we treat the galactic center as a sort of prototype of the LISA targets, and of course then we're very interested in understanding what's happening there. Now, I also want to point out for future reference that the relaxation time scales, sorry, this is the rate, so the relaxation time, which is 1 over the rate, scales inversely with this product of the number density of objects times their mass square, which means that in this, if you have a variety of masses and you take some average of them, it will be the more massive objects that will dominate, even if their number density is significantly lower. Now, another consequence of being in a relaxed cusp or relaxed system is that your stellar density profile develops its quasi-steady thermodynamical end state is a cusp, that is, you have diverging density towards the center, which means that in the low mass the systems around low mass black holes, which were already to start with more dense on the average, since you have a rising density towards the center, they will be very, very dense close to the black hole, where things that happen to EMRIs are particularly relevant. This can be easily derived, I won't do it in detail, by simply assuming that the energy that the system loses when a star gets deflected into the black hole and goes essentially out of the system is carried away in steady state by the gravitational binding energy of the other stars. And then if you assume steady state, you can easily derive it in this simple formulation that if you have one type of stars, say with typical mass m star, you get a cusp, a parallel cusp with this particular index. So you have n going as r to the -7/4. So these are the obvious implications, and if you have a very dense system, you have also very high rates of massive black hole, star-star interactions, which means that you have lots of interesting physics going on. Now, there has been this reasonable and rather seemingly robust view of the universe has undergone quite a shock when finally, after a very long time where people were attempting to measure this density distribution in the galactic center and using incrementally better and more refined methods, we now know without any shred of doubt that in fact the red giant distribution, and these are bright stars, bright enough to see, we don't see most of the stars in the galactic center, only those bright enough. And the red giants are all stars and therefore should have in principle undergone relaxation processes and do not show a cusp. Maybe they show a flat core, maybe even there's a cavity in the density distribution around the galactic center in terms of these red giants. Again, these at best are just tracers of the population. They're definitely not all the population. Now, as I've just argued, there's a very robust chain of inferences which tells us that if a relaxed system has a high density stellar cusp and vice versa, this is an if and only if situation. The fact that we don't see a cusp, or from this we immediately see that a system without a cusp cannot be dynamically relaxed. And obviously an unrelaxed system depends on its initial conditions, which may vary hugely between galaxy and galaxy. Now, this is a bad situation for theory in terms of predictive power. If a system is relaxed, we can hope, with hard work, to understand its dynamics from first principles. It's a well-defined system. If it depends on initial conditions, we may have to resort to merger trees like, say, Marta has been showing us, and have only very vague and fuzzy statistical things that we can say about galaxies. So these are the observations. The interpretation is then left for us to say whether there is in fact an underlying cusp of stars that cannot be observed now. So I'm calling it a dark cusp. It has nothing to do with particle dark matter or anything mysterious. It's simply a cusp made of low mass stars and stellar remnants, which is still there. And we have, in effect, not a problem with the system not having a cusp, but a problem with our tracer stars. And this could be, Melvin, for example, described one mechanism where we could selectively make the red giants go away. In fact, to do that, we need to have a dark cusp. But the jury is still out on that. I have my personal prejudice that there is a dark cusp, but it's just a prejudice at this point. If we take at face value that there is no cusp, and the galactic center is not relaxed, so we can ask ourselves, since this is our poster galaxy, are any galactic centers relaxed? Maybe they all have undergone, say, some major mergers of the type that David has been studying. And of course, as I mentioned, if they're unrelaxed, we lose a lot of our predictive power. So this is what's at stake now. And it will all hang on our ability to get a handle on what exactly is there in the center of the galactic center, beyond those quote-unquote easily viewable giants, which we know are not in the right numbers that we expected. Okay, so this was to focus why all this is very important, and I would say almost even urgent for us to understand. So here is a list of, since specifying the relaxation state and properties of the galactic center and galactic nuclei of the type that are relevant for Lisa is so important, I've listed here various types of relaxation processes that play some role in EMRI dynamics, also in the dynamics of equal mass mergers, processes from which we can get some handle by observations of the galactic center, but not only observations of other parts of our galaxy and of external galaxies. And that together, we hope that we will get enough constraints to start understanding what could occur and what couldn't occur in EMRI dynamics. Now this is a long list. I'm not sure I will be able to go through all of it, but I'll try at least to get you the highlights. So before even we go into the more exotic relaxation processes, I'd like to very quickly introduce the concept of the loss cone, which is essentially has a very visual origin. So this is the black hole here, and there's some region around the black hole where, if your object comes close enough, interesting things that you're interested in happen. For example, if it gets captured, it becomes an EMRI, or maybe the star is the white dwarf is totally disrupted, or whatever. And your star is here, and it could get to that red region either by losing energy, or what turns out to be much quicker, by changing its angular momentum from going on a circular orbit, say this direction, to going on an almost radial orbit. And the types and the time scales for each of these two changes are related in the following way. So the time to change the energy, say by order unity, is usually a very slow time, but the time to change the angular momentum by order of itself is scaled to the circular angular momentum, which is the maximal angular momentum that is possible at a given energy. And so if you're already by some other process at a lowish angular momentum, you don't have to be at any kind of extreme orbit, but even if this, say, is a tenth of the circular angular momentum, you're already, the time it will take you to scatter all the way to the black hole is 1/100th of the time it will take you to lose energy. So when you analyze in a statistical way what's happening, you can plot it conceptually on these plots. These are completely equivalent to the plot that David has shown his numerical results on, but David chose to express eccentricity, to express angular momentum by 1 minus the eccentricity, and to express the orbital energy by the semi-major axis. This is closer to the way that the analytical calculations are done, and so I prefer to look at it this way. So the red part in this diagram represents to us orbits with energy and angular momentum that are inherently unstable or already inside the black hole. The blue region is where stars can exist. And in the absence of any dissipative mechanism, and if you just consider two-body relaxation, what will happen is that your star will scatter, once it's still at very close to a circular orbit, it will scatter both in energy and angular momentum. At a certain point, by chance, it will be driven to lower angular momentum. At that point, the relative change in angular momentum, this is log scale, so the relative change in angular momentum becomes much faster than in energy, and it will fall into the black hole. And David, in fact, showed us yesterday a simulation which does just that. Although there, the driving force was not two-body relaxation, but it was the same type of trajectory. If you add a dissipative mechanism, obviously the one we're interested in is gravitational wave, you find that if you get too close to the last stable orbit, which is here designated simply as the angular momentum of the lost cone, then you undergo some transition where the deterministic, so to speak, energy dissipation becomes much faster than the stochastic J scattering, and you're basically carried along this orbit until you almost reach disruption, and then there is a narrow band where your period is high enough to be relevant for LISA. Now, it turns out that when you introduce such an in-spiral, you can basically divide your phase space into two parts. One which is the part where you can actually complete this, and in another further away at lower energies where you still execute this kind of scatter, because you spend a long time circling the black hole, and over that long time you can pick up enough scattering in J to be thrown directly into the black hole. And this is known as the critical energy or critical semi-major axis, or more roughly as the critical radius. So if you want to make a crude but rather I think reliable estimate of the EMRI rate, what you need to simply find out is what is the critical radius for the particular relaxation mechanism that you are assuming. Find out how many stars lie above this yellow line. And sorry, I guess I've been talking too long. And divide it by the relaxation time. This comes to be with very high, depending on different assumptions that go into this, comes out to be anything between 1 per billion to 1 per million years per galaxy. So, already understanding this process can give us some handle on the distribution of eccentricities of stars as they enter the LISA band, under the assumption that it's a single star being scattered into the black hole under the influence of uncorrelated two-body relaxation. So I'll just mention that you find that in fact you expect a rather highish eccentricity distribution from this kind of process, which means that your waveforms will typically look the more messy and complicated ones rather than the very regular ones. Another thing that is related to two-body relaxation was already mentioned in the first day is the strong mass segregation, which very briefly, and this is I think a situation very similar to the one that Lior was describing, where LISA without flying has already pushed the field forward, because this was not the existence of this second type of solution for mass segregation was not known. But in fact, it may actually be the way that nature usually chooses, because it turns out that old stellar populations, whether they are old and passive or continuously star forming, tend over time to polarize in two mass groups. So you have on one side the stellar black holes, on the other side you have everything else, which is of the order of one solar mass, so a factor of 10 difference roughly in the mean mass. And in such a case, and you can calculate it here with specific models for star formation. In such a case, this power law here, which for a single mass was 7/4, which means that this PM was a quarter, actually can be driven to much higher values for the massive object. Basically, the massive object sink by the under dynamical friction into the center, and instead of having, this is, by the way, what's plotted here are the indices. So this is not a plot of density. This is the plot of how steep would be the distribution. This region, where the values are low, maybe as low as a quarter or so, this is what was studied 30 years ago for historical reasons which I don't have time to get into. The people who studied this, Bakal and Wolf, could have actually, had they chosen, discovered the strong segregation half of the solution space, but they were focused on this, and they thought that this was a universal solution. In fact, our galactic center perhaps lies here, so the stellar black holes in the galactic center are expected to have even higher density, of course, because we do care what is the degree of crowding of sources in the center inside the critical radius. This can play a role, and in fact may actually increase the EMRI rate by a factor of 10 over what you would get if you simply assume the old but probably incorrect segregation solution. And by the way, this segregation solution was also verified independently by work done by Miguel and Pau, by N-body, which is a very, very reassuring. Yes.
Can you just explain again what's the difference between weak and strong?
Simply the matter of how different the slopes are for the light stars and the...
Right, what's the physical process?
The physical process is that if you have a very high number of massive objects, they tend to scatter against each other. Basically, the low mass stars are just spectators. They don't really play a role, and this is essentially like the single mass solution, which we saw can be actually shown to be r to the minus 7 quarters. But if you have enough light stars, then they basically, the heavy stars don't scatter so much against each other. They pull against the lighter stars, and they sink in a much more effective way to the center. That's the physical understanding of this process. So, given that time is running, David already talked about residual relaxation. I won't. I hope you remember it. It was only yesterday. So basically, this is a case. Yes, 5 minutes. Yes, this is the case where, if the potential is very regular, for example, around the point mass, the orbits tend to evolve very slowly, and so a test star will then feel strong torques, and in fact, it will be torqued and scan all possible ranges of angular momentum up until to the time on which the process stops being coherent, and there are deviations from the symmetry. For example, the fact that it's not a Kepler orbit, but there are stars around, or GR precession, will eventually limit the coherence time. And so this coherence time then becomes the accumulated change in angular momentum over the coherence time then becomes the new very large step size of an accelerated random walk. So that's why this process can be many orders of magnitude faster than normal to body relaxation, changing the angular momentum of stars, and the way it can change depends on the symmetries of the potential. So in some cases it can change both the direction and the magnitude of the angular momentum, in others only the direction of the angular momentum. But in any case, it is inversely proportional to the coherence time. If the coherence time is long, the relaxation is fast. So let's look again, in light of what David showed us yesterday, at this phase space for in-spiral. So back in 2006, when we looked into this problem, there was no hope of actually doing n-body simulations of the type that David is doing today. We had to resort to analytical arguments using a framework where you basically assume that your test star and your background it's just a didactic separation, because there's nothing fundamentally different between the star chosen to be your test star. The test star and background are essentially sampling the same orbital properties, and we realized that in fact the residual relaxation can be something which is too good in terms that it actually will drive stars very efficiently on this axis all the way to a plunge orbit. And we realized that the nature may be actually generous to us by having this process of GR precession quench the effectiveness of rest relaxation once you get to this corner of phase space, which is basically when the things become relativistic. And we assume that there will be a transition to a regime where the orbit is again dominated by the slower non-resonant relaxation, which will allow the star to percolate gently into the EMRI orbit and execute clean two-body classical EMRI motion. So when we were thought about this, we were worried that the precession may not be effective enough, and that in fact, maybe because this requires fine-tuning of the two processes, one is dynamical, the other is intrinsic to GR. And we were afraid that in fact, maybe all stars will become plunge. What we did not expect was that the problem is in the opposite direction. In fact, rest relaxation, or the quenching, is too strong, and it's strong in a non-trivial way, which actually makes stars bounce from the barrier back here, and very few actually manage to cross the barrier, which is a completely new result from the last, I don't know, few weeks or even less, and it's quite a rude surprise. Okay, so I wish I could have had time to show David's film again, movie again, but I'll just go on to. So this is a very informal conference, and so I have the courage to show you results that are just a few hours old. And I think I'm optimistic that this may be the explanation for the bouncing problem, and Ben has been working hard on this to try and see how this can be incorporated into the statistical description of the process. And basically, what I think is happening here is the following.
Actually, I saw you at the restaurant working.
So, yeah, I know. This is true. I'm not making this
It's
up.
live.
So imagine that we have a star that is orbiting in the plane of this of the board of the screen, and because it's on a very relativistic orbit, it's already precessing due to GR in say the sense given by the curved arrows. Now this
Napkin bullet.
it is there are indications that it is possible to approximate the force that it feels by the ambient distribution of stars as a fixed field force. And because of the symmetry, the torques on these ellipses are can be calculated very simply by taking the lever arm from the focus of the ellipse to the center of the ellipse, which is given here. It's proportional to the same major axis times the eccentricity, and multiply it by the force. So the torque here is R cross F, which is, let's suppose on this side it happens to be proportional to the angular momentum of the orbit, and on this side, by symmetry, since we have reversed the sign of R, it will be proportional to anti-proportional or anti-aligned with the angular momentum. Now, on this side, since it's aligned, it will increase J, thereby decreasing the eccentricity, making the orbit rounder. Now, the precession rate depends very strongly on the eccentricity. In particular, it diverges in the region near eccentricity 1, which is where we are interested in it. So even making it a slightly bit rounder will actually increase the time that you spend in this half of the orbit, of the precession orbit. And the converse is true for the other side. Now, you could worry about what's happening to the lever arm, which is also a function of eccentricity, but it varies very slowly, just linearly, and it never diverges. So when E is close to 1, you're basically increasing the time spent at the region where the torques are working towards decreasing the eccentricity, and you're rushing through the part where the torques are working to increase the eccentricity. We actually wrote down the differential equations describing it, and we get a very strong asymmetry. Orbits tend to run away back from, and if you remember David's animation, they go to the barrier and then sort of bounce and run away from it. I think this explains it. So we of course have to look at this a bit more carefully and compare. So 0 time. Okay, so let me just then rush. There's lots of interesting stuff. You should talk with Ben about what the. I'm making a little ad here. What the S stars in the galactic center tell us about the way that we populate orbits close to a black hole. It's very relevant for EMRIs. And let me just flash on my my conclusions, and I'll take questions. Thank you very much.
Questions?
Can you go back one slide to where you put the measure? Oh, one more. There. Can you say maybe a paragraph about the work in the NGC 4258
Yes.
disk?
So, what this basically is an attempt to try and find physical systems where resonant relaxation can be measured and verify, or first of all, test our basic idea that it actually works. Also in nature, that there aren't no showstoppers. Say that the symmetries we assume are actually never there in real systems because of various, astrophysical complications, and also to calibrate various order of unity kind of prefactors that creep into an attempt to write an simple analytical description of resonant relaxation. So there's information from simulations from the galactic center, but here what we found was that you can give a very natural explanation of the magnitude and scales, time scales, length scales of the maser warp, the warp observed in the maser disk of NGC 4258. If you assume that it's being torqued by the stars around it, so you just assume the M sigma relation. You have some. We know the mass of the black hole from the dynamics of the disk. We match it through the M sigma relation to some typical density of stars around it. We plug in the estimates for the type of resonant relaxation that can change direction but not eccentricity, which is the one relevant here. And we find that it could warp, create this warp. And we're now working on doing this in an even more elaborate way, including also Bardeen-Peterson precession and other complications.